Morning, everybody. So let's go ahead and get started here. We didn't quite get through everything that we needed to get through last time, so I've included a little bit more in these slides to kind of cover some of that material because on my Part B screencast it was kind of fast, so we'll go over some of that stuff again. So what's SN1 mean? Unimolecular what? What's S? What's N? What's 1? Unimolecular. What's SN2? Okay. The rate of an SN1 reaction is proportional to what? What is the word? The bird is the word. What appears in the rate equation? Concentration of what? No, there is a constant, but that's, huh? The alkyl halide, right? So SN1 reactions, the rate is proportional to the concentration of the alkyl halide, not the nucleophile, right? What is an SN2 reaction in terms of its rate? What's it proportional to? Don't forget we have a test next Wednesday, right? Which is a week away. This stuff should be coming to you. What is an SN2 reaction proportional to? Both species appear in the rate equation. That is exactly right. Right? It is a second order overall reaction, whereas an SN1 is a first order. How many steps are in an SN1 reaction? 2 steps. How many steps are in an SN2? 1. All right, very good. So today we're going to talk a little bit more about things that really get into SN1 chemistry a little bit because we're talking about carbocations. And the carbocation in an SN1 reaction is referred to as a what? We say the alkyl halide goes through an energy of activation. You generate a carbocation what? What do we call that? It is a slow step. That's true, but that's not the word I'm looking for. It is an intermediate, right? And what do we mean by an intermediate? Doesn't stay that way very long, right? It's intermediary on its way to something else. It exists. We can detect it. I cannot grab a bottle of carbocations off the shelf. They're highly reactive species. They exist for a very fleeting amount of time, okay? But they do exist, okay? So we're going to talk about carbocation stability. There are some carbocations that are very stable. There are some carbocations that are hardly stable at all. That does not mean, it's a relative thing, and I know you all hate relative arguments, but that's science, okay? Just because a carbocation is stable does not mean it is bottleable. Okay, it's all relative. Okay, this carbocation is much more stable than that carbocation. This is not an absolute argument. Okay, we're going to talk about things that affect both SN1 and SN2 reactions. You will need to be able to distinguish whether or not a reaction most likely will go through an SN1 or an SN2 reaction. Okay, and we probably won't get to talking about at all elimination reactions today, so we'll save that for another time. Okay, so we talked last time that an alkyl halide, the leaving group can leave in the slow step, not involving the nucleophile at all, and generate a carbocation. That carbocation is what kind of hybridization? What's the hybridization of that carbon? It is sp2. What is the geometry of it? It is trigonal planar. Okay, very good. We're warming up. I like that. All right, so it's a trigonal planar carbocation. The orbital on that carbon is a what orbital? It is a p orbital without electrons, right? It is a vacant p orbital. All right, very good. We're warming up. I like it. Okay, so that's the slow step, right? And then the fast step is where the nucleophile comes in and reacts with the carbocation to give the new bond, right? And so basically the overall functional group transformation here is an alkyl halide into an ester in this particular case. because the nucleophile was an acetate anion. Okay? So far we've learned that we can convert alkyl halides into alcohols. We can convert alkyl halides into thiols. We can convert alkyl halides into nitriles with cyanide. We've learned we can make amines. You've all actually learned a lot of chemistry from SN1 and SN2 type stuff, okay, in terms of functional group transformations, okay? Now, it turns out that the rate of an SN1 reaction is proportional to the stability of the carbocation. The more stable the carbocation that you're forming, the faster the reaction will be, okay? And that comes down to the Hammond postulate, which we'll talk a little bit about in a second. But basically, when we observe these reactions, what we notice is that if I have a methyl alkyl halide, the reaction's extraordinarily slow. It doesn't occur hardly at all in an SN1 reaction. However, if I have a tertiary alkyl halide, the reaction is quite quick, almost over instantly sometimes, okay? And then everything else is in between. So what you can find is that methyl, very, very slow. Primary is extremely slow. Secondary is slow but acceptable. And tertiary is the fastest, okay? So tertiary alkyl halides undergo SN1 reactions very rapidly. Secondary, it's okay. Primary and methyl, it's so slow that we say it doesn't occur. In fact, if I took methyl iodide and I placed it in water, okay, which would require it to go through an SN1 chemistry, it would sit here for hundreds of years. It's slow, okay? It's because the methyl carbocation is not stable at all, whereas a tertiary carbocation is quite stable, okay? Relatively speaking, okay? What you're going to notice in terms of the things that you need to just kind of commit to memory, the kinetics of an SN1 reaction are first order. It only depends on the species that gives rise to the alkyl, or excuse me, the carbocation. In this case, it's the alkyl halide. The alkyl halide reacts, the leaving group leaves, right? You get a carbocation intermediate. That's what the kinetics are involved with. The nucleophile doesn't come in. The mechanism is two steps. The stereochemistry, right? We get a trigonal planar carbocation. Now, the nucleophile has what kind of options for attack? It can either attack from the top, because remember, there's a p orbital that has lobes on both sides of that plane of those atoms, right? So the nucleophile can come in from the top, or it can come in from the bottom. And if the halide is completely removed, then the odds are what? 50-50, and we'd end up with a racemic mixture. That's right. Would it rotate plane polarized light if it's racemic? No. However, in that part B that I put on the YouTube channel, right, does the halide always get completely out of the way before the chemistry occurs? No. And so the halogen leaves, it can only leave from one side because it doesn't exist on both sides, right? And so if you're a nucleophile, you want to get close to a bromide or get as far away from it as possible. You're going to want to get as far away as possible. So SN1 chemistry, we can actually see racemization or partial what? Partial inversion, right? Because the nucleophile would prefer to come in from the opposite side of the leaving group, but sometimes it'll come in from the same side as the leaving group. And so it's not going to be 50-50. SN2, however, must always be what? In terms of the stereochemistry. It's always inversion. It's 100% inversion of that stereocenter. Okay? So if you start off with an S stereocenter and it's going through SN2 chemistry, it's going to be 100% R. It's going to go from S to R. It's going to invert 100%. With an SN1 reaction, that leaving group will leave and you will end up with either complete racemization or partial inversion. Okay? And those facts have been used to determine whether or not certain reactions are actually SN1 or SN2. They've used stereochemistry arguments to figure this out. You can actually go down to my laboratory and use my polarimeter, put the reagents inside the polarimetry cell and watch the rotation change. And if it's complete inversion, it'll go from positive to negative if you set the chemistry up right. And you can follow it through polarimetry. So that's kind of cool. The more substituted the halide, the faster the reaction. So we find that the rate is fastest for tertiary alkyl halides, then secondary alkyl halides, and primary and methyl. We say they really don't react. So really this chart should have a greater than, greater than, greater than, greater than, greater than there, okay? Much, much greater than, all right? And so this all comes down to carbocation stability. A tertiary carbocation is more stable than a secondary, is more stable than a primary, is more stable than a methyl. Okay? Now, if you think about it, a carbocation is deficient in what? It's deficient in electrons. It's on the second period. It would like to satisfy the octet rule, and it only has 6 electrons around it. So anything that we can do to help give it some electrons, I'm going to put that in air quotes, is going to be a good thing, right? It's going to be a stabilizing factor, okay? And so it turns out that tertiary carbocations can get some electrons from the neighboring alkyl groups through space, okay? It's hard to draw resonance structures for it, okay? It's called a hyperconjugation effect, and we'll talk a little bit about that in a moment. But if you look at the electrostatic potential maps, you can see that this is true, right? Remember in the electrostatic potential maps, blue means a lot of positive charge. Well, there's methyl. That's pretty darn blue. And there's a tertiary carbocation. That is just faintly blue. It means that this positive charge has been spread out throughout the molecule a little bit. And that's a stabilizing effect, okay? So tertiary carbocations are stable. Secondary carbocations are less stable than that. Primary, much less stable. Methyl, way less stable, okay? Now, when you tell somebody that you can't generate a methyl carbocation, when you tell a chemist that, they go into the lab and spend years and millions of dollars trying to prove you wrong, okay? And back in the day when the federal government was actually giving a lot of money to grants, people went in, and there was this guy named George Olaw, Nobel Prize winner from USC, Southern California, excuse me. He developed these things called magic acids. That's a nice term, isn't it? Magic acids. And he was actually able to generate methyl carbocations. And he won a Nobel Prize. Okay? But it's not normal types of chemistry that people would use. You would not use this industrially. These were expensive things. He just tried to show that it could be done under the right circumstances. And he did. Okay? But for the purposes of most normal kind of situations, methyl carbocations and primary carbocations cannot be generated. Okay? Now, if we look at a methyl carbocation, you all mentioned to me that a carbocation is trigonal planar, so that means that everything that's attached directly to the carbon atom lie in the same plane, right? All 3 of these atoms lie in the plane of this carbocation, right? And the p orbital goes above the plane and below the plane. We have this blue lobe that you see, and we have this red lobe, and those are just mathematical signs because it has to go through a node in the center, right? So they're just mathematical operators, okay? Don't need to worry about that. Okay? The electrons in these carbon-hydrogen bonds here are in the plane of the node. So can any of these electrons actually be donated into the p orbital? No. Geometrically, it's impossible. Okay? However, if we put an alkyl group on the molecule, and here we have a secondary carbocation. Okay? They just chose to do that one. Okay? So the electrons between the carbons can't be donated into the p orbital, but notice that these CH bonds kind of look like a p orbital. They're a lopsided p orbital, but they kind of look like a p orbital. There's electrons there, right? And it turns out that they kind of touch, barely touch, the p orbital. And so some of those electrons can actually be bled over into the carbocation, quote unquote, bled over, okay? And so this is called hyperconjugation, and it's the more of these interactions you have with the carbocation, the more stable it is. In a primary carbocation, you would just have one. In a secondary carbocation, you'd have another CH bond here that could do the same thing, And in a tertiary, you would have 3 of them. And so the more electrons we can donate into that carbocation, the more stable it's going to be, right? And that's going to be a good thing. So this is called hyperconjugation. There are some books that try to show this as resonance. You cannot do that. And I hate that they show you that way. Why can I not show this as resonance? Because if I move the electrons between that carbon-hydrogen bond, that's a sigma bond, right? If I move those electrons over to try to show resonance, I have to move an atom. We cannot move atoms in resonance structures, remember, only electrons, okay? So this is a hyperconjugation effect. It is through space, and it is a stabilizing effect, okay? So what we notice is that when we do these reactions, if we take a tertiary alkyl halide and we run the reaction, it goes really, really quick because we're getting a tertiary carbocation. If we set up basically the same reaction where we're starting off with a secondary alkyl halide and run it, we'd find out that the reaction goes slower. If we start off with a primary alkyl halide, we'd find out that we're going to be here a really long time. And if we start off with a methyl halide, we're going to find out we're going to be here forever. And then your grandchildren's forever, and your grandchildren's grandchildren's forever. Okay? Lots of forevers. Okay? Because the chemistry just doesn't happen. Okay? And so this brings us to the Hammond postulate. Okay? The Hammond postulate states that the transition state of a reaction will resemble the structure of the species to which it is closest in energy. What is the transition state? What do I mean by that? What is a transition state? The carbocation is actually an intermediate. Intermediates are different than transition states. If I was to draw it here, so here's my starting materials, here's my carbocation intermediate, where's the transition state? Where? On the... Be brave. Where's it at? At the peak. Right here is the transition state. It's the equivalent of me having you climb the TV tower in Berlin and standing up on the very top of the antenna. How long do you think you're going to be able to stand there? You're going to fall off real quick, right? It is the top of the mountain, and any little vibration makes it fall down, just like you standing on the TV tower in Berlin would do, okay? And so you can't bottle it. It's hard to study. We really don't know what many of them look like, but we can take a guess. The Hammond postulate allows us to take a guess. Which species, the carbocation or the alkyl halide, is closest in energy to this? The carbocation. This tells us that the transition state should look more like the carbocation than the starting material. Okay? We know what carbocations look like. They're intermediates. We can observe them if we have fast enough experiments to observe them. But we can't observe them. We can get information about them. Okay? So we know that the transition state should look more like the carbocation than the alkyl halide. So if you were going to draw the transition state for the formation of a carbocation, what might its bond angles look like? What would they become closer to? And what is the carbocation's bond angles? 120. It looks more trigonal planar, right? The alkyl halide is sp3, 109 bond angles, right? So you're going to draw something that looks more like that carbocation than looks like the starting material, okay? And so basically what this means in terms of rate, if I have a stable carbocation, which is the blue line, and I have an unstable carbocation, relatively speaking, which is the red line, which one of these would be the fastest? The one that requires less energy. Very good. The blue one. because that transition state should look more like this carbocation. And this carbocation is lower in energy, so that's going to lower the energy of activation. Okay? It's easier to form that more stable carbocation. Right? So the energy of activation is less. Think about your everyday life. If something is easier, are you more or less likely to do it? You are more likely to do it, right? People typically don't do hard very well, right? We like things to be easy. Okay? So the same thing in chemistry. Chemistry is actually quite lazy, right? And so it turns out that the easier it is to form a carbocation, the faster that reaction is going to go, because the Hammond postulate dictates that the energy of activation will be lower. Okay? Does that make sense? Okay? It is a very simple concept, but when you apply it, it can be tricky. Okay? But the take-home message here is that the kinetics are dictated by the stability of the carbocation because of the Hammond postulate. Okay? You will learn a lot more about that when you get into physical chemistry if you're a chemistry major. You will learn how to do the math to figure that out. Okay? I'm not terribly interested in you knowing the math at this point to do that. I want you to understand the concept. Okay? I want you to be connected to that concept. SN reactions also depend on the nature of the nucleophile. Now, you might be saying, well, SN1 reactions don't. Not in terms of the rate, but the type of nucleophile you have can determine whether or not a reaction goes through an SN1 or an SN2 reaction. Okay? And it turns out, you need to know this, really good nucleophiles favor SN2. Really poor nucleophiles favor SN1. So the nucleophile does matter in terms of what kind of reaction mechanism is occurring, especially for secondary alkyl halides, which can do both SN1 and SN2. Okay? Even though they don't necessarily always appear in the rate equation. Okay? So, if we have a nucleophile, or let's say we have two nucleophiles, typically the stronger nucleophile is the one that's the stronger base. Basicity typically follows nucleophilicity. Or I should say it the other way around. Nucleophilicity typically follows basicity. However, all nucleophiles are Lewis bases, but not all Lewis bases are nucleophiles, and we'll see some examples. So for example, if we looked at hydroxide and acetate as being a nucleophile, hydroxide is oxygen minus, acetate has oxygen minus. They're both negatively charged. They're both decent nucleophiles. But hydroxide is going to be the better nucleophile because it's the stronger base. Acetate is the weaker base. Okay? A negatively charged nucleophile is always stronger than its conjugate acid. Hydroxide is a better nucleophile than water. Okay? As you move from right to left across a period, nucleophilicity increases because basicity increases. F minus is a poor nucleophile. Hydroxide is better. Amide is better. CH3 minus is way good. This is a strong nucleophile, good nucleophile, weak nucleophile. Okay? The other way to think about it, because you all like to think about going from left to right most of the time on the periodic table, just reverse it. Nucleophilicity decreases as I go from left to right. That's the way I think about it. The book likes to propose it this way. Okay? Does that make sense to you all looking at that? And why does that make sense? Why would F minus be a worse nucleophile than hydroxide? That's right. Fluoride being electronegative, it wants to hold on to its electrons. It's stingy. It doesn't want to share them. Hydroxide, oxygen is less electronegative than fluoride. It's more willing to share those electrons. Right? Nitrogen is less electronegative than oxygen. It's more willing to share its electrons. And carbon is less electronegative than nitrogen. It's more willing to share its electrons. Right? So I think it does make good sense. So let's do a little thought experiment here. Anna here starts off with this alkyl halide. How would she name that? Bromocyclohexane, perfectly fine. How else could we name it? Cyclohexyl bromide would also be another good use for this. What kind of alkyl halide is it? Primary, secondary, or tertiary? It is a secondary alkyl halide. Okay? We are going to react that with a mixture of sodium hydroxide and sodium acetate. So we've got two nucleophiles that are competing for the same electrophile, the same alkyl halide. So I've got 1 mole. Let's just set it up like this. I've got 1 mole of the alkyl halide, I've got half a mole of sodium hydroxide, and I've got half a mole of sodium acetate. And I mix these in some solvent that dissolves everything, and I wait to see what the chemistry gives me. What are the possible products that I would get out of this reaction? So I'd go from an alkyl halide to a what? If sodium hydroxide was the nucleophile, what would be my product? Pardon? Well, not a phenol, because that's not an aromatic ring, but ol is, which is an alcohol, right? Yeah, so it would make cyclohexanol, right? What would happen if we were reacting this with the sodium acetate? C double bond O, O minus. Okay, we'd end up with an ester, right? So we'd go from alkyl halide to alcohol, we'd go from alkyl halide to ester, and we would end up with the alcohol being the major product, and we would end up with the ester being the minor product. Now, could you predict that it would be 90% of the alcohol and 10% of the ester? No, I don't expect you to know it at that level this point. You get up into the 300-400 level classes, you get up into graduate coursework in chemistry, we'd start to expect you to be able to predict better than that. Right now, if you can predict major and minor, I'm great. What defines something as major? Huh? Greater than 50%. What dictates minor? Less than 50%. That's good enough for me right now. Okay, if you can get that, that would be good enough for me. Okay? Now, we mentioned that the cardinal rule, actually I shouldn't call that the cardinal rule, I've got another cardinal rule later. But our golden rule of nucleophiles, right, is that all nucleophiles are Lewis bases, but not all Lewis bases are nucleophiles, right? And so if we look at these two molecules, notice we have oxygen with a negative charge on both of them. When we look at the pKas only differ by a couple of pKa units. Ethoxide has a pKa of around 16.5 or something. Tert butoxide has a pKa of just a little over 18. They don't differ by a lot. They're both decent bases, but only one functions as a nucleophile, and it is the ethoxide. Tert butoxide is not nucleophilic. It is what we call a non-nucleophilic base. Okay? Why would tert butoxide be a strong base and not function as a nucleophile? Tert butoxide will react with a proton faster than ethoxide, but it won't function as a nucleophile. Why might that be? There's a bunch of crap around it. Let's just keep it simple, right? We call that steric hindrance, okay? Steric hindrance is if I ask somebody here to run through all of you to get to the end. You all are in the way. You slow that person down. If I move you all out of the way and I tell the person to go to the other corner, they can get there really quickly, right? The same kind of thing happens here. So let's suppose, for example, we wanted to react methyl iodide with these two nucleophiles, right? So if it's ethoxide, this is going to be an SN2 reaction. The nucleophile has to come in from the back side and attack, right, to give us our product. In this case, we would get an ether, right? No problem. Okay, so if I asked Savannah to come into the lab and do this reaction, she'd be able to do this reaction no problem. But if I asked John to come in and do this chemistry, I can push the arrows on paper. Not breaking any rules here. He would be there for a really long time. In fact, almost forever, because their chemistry just wouldn't occur. These groups, right, get in the way of the chemistry. And you got to build a model to really see it. It shields that oxygen. So when this tries to come here, this oxygen actually has to physically touch that carbon. And all this stuff is blocking it from doing that. Okay? The more stuff you have around a nucleophile, the more bulky it becomes. The more steric hindrance you have, the slower the reaction will be. And this reaction is really slow. Okay? This just has one carbon atom. Okay? So yes, there's some steric hindrance, but not like this one. Okay? This chemistry will occur. This chemistry will not. So the more stuff you put around your nucleophile, the worse the nucleophile is going to be. So, nucleophiles matter, especially in SN2 reactions, right? So if I gave you this reaction, I asked you to predict which one was fastest, you need to be able to do that. You would predict this is the faster one of the two, right? Given what we know about steric hindrance, okay? There's also a solvent effect in this type of chemistry. So let's suppose we want to use bromide Br- as a nucleophile. So let's say we have an alkyl chloride, we want to react it with bromide and make an alkyl bromide. We can do that. Chlorine would be the leaving group, the bromide will come in and be the nucleophile. We can draw arrows to do that, okay? But what you're going to find is that solvent matters in that reaction, okay? What I just described would be an SN2 reaction, and solvent matters. Sodium bromide is a salt, and it is soluble in what really well? Water, right? Going back to general chemistry here a little bit, right? When you place a salt into water in general chemistry, you would write Na plus, aqueous, plus Br- aqueous. What does that aqueous mean? It means it's soluble in water, but what does it really mean? It means that water is surrounding those ions. They are being solvated, okay? It doesn't just mean that it's in water. It means that water is associating with the ions. And so sodium plus is having interactions with the oxygen atoms. Sodium plus is a cation. It would like to have some electrons. Where can it get them from water? From the lone pairs of oxygen, right? And so you have these coordinate bonds. And so sodium is being surrounded by water. Bromide has a negative charge. It would like to interact with the positive side of the water. Remember, water's a dipole. We have a positive end and a negative end, right? And so water forms what look to be like hydrogen bonds around the bromide. Is that going to make the chemistry work faster or slower? Slower. This is just like steric hindrance, isn't it? If the bromide has to approach a carbon atom, all this water's in the way. What has to happen to that water? It has to get out of the way, doesn't it? Right? It has to get out of the way before the chemistry can occur, because if this approaches a carbon atom, the water's going to bump into it. So the water has to come off before the chemistry can occur, and that slows it down. Yes, it makes the sodium bromide soluble, but it slows the reaction down considerably because it is solvated. It is the same thing as putting a protecting shell around it, if you will, a shell of protecting water, okay, by these stronger hydrogen bond interactions. Okay? So, what can we do? Savannah doesn't want to be in lab till midnight waiting for a reaction to occur, so what can she do to speed the reaction up with sodium bromide? You can use a You're almost there. We're going to have to use a polar solvent. But I'm going to need to have one that's non-aqueous that doesn't form these hydrogen bonds. Okay? And so we have two classes of solvents that you need to memorize. We have polar protic solvents. Okay? A polar protic solvent is any solvent that is both polar and has protons, hydrogen, that are attached to things like oxygen and nitrogen. Water is a perfect example. It is a polar protic solvent. It can form hydrogen bonds. Alcohol has OH. It can also form hydrogen bonds with the bromide. It is a polar protic solvent, and it too will slow the reaction down. Okay? And so what you find is that as you go from left to, from top to bottom in a family, right? Fluoride, chloride, bromide, iodide. Iodide is the better nucleophile. Fluoride is a horrible nucleophile. And it's because this doesn't solvate as well as fluoride. Fluoride is tiny. It's got a negative charge that is very concentrated into a small space. The solvent forms around it very, very tightly. It forms a very, very tight solvation shell, as we call it. It doesn't like to get rid of its water. Iodide is bigger. That same amount of negative charge is located over a much larger area. The water does form a solvation shell around it, but it's very weakly bound, and it can come off really quickly, really easily. So iodide is actually a very good nucleophile. Bromide is an okay nucleophile. Chloride, and fluoride not hardly at all, in a polar protic solvent. Okay? We also have what are known as polar aprotic solvents. These are solvents which are polar. They have dipole moments, but they have no hydrogens on atoms like oxygen and nitrogen. They cannot be hydrogen bond donors. They can accept hydrogen bonds, but they cannot donate hydrogen bonds because they have no hydrogens on things like oxygen or nitrogen. Here are some examples. You need to commit these to memory. You need to know these by both name, structure, and abbreviation. Acetone, fingernail polish remover, ladies. Polar aprotic solvent. Acetonitrile, a polar aprotic solvent. Tetrahydrofuran is a polar aprotic solvent. It is an ether. It's cyclic. It's known as THF. You will hear me refer to it as THF. Okay? DMSO, dimethyl sulfoxide. Kind of looks like acetone, except instead of carbon, there's a sulfur there. It's a very good polar aprotic solvent. We use it a lot. DMSO, for those of you in athletics or have been involved in athletics, they used to use DMSO to deliver pain meds to athletes at their muscles because DMSO will dissolve a lot of stuff and it will transport it through your skin very, very easily. Okay? We use DMSO a lot to do cyanide chemistry because sodium cyanide is soluble in DMSO and it promotes the chemistry, but it's also dangerous because if I touch the DMSO solution, it will transport cyanide through my skin. And if I get enough transported through my skin, I'll die. So you have to be very careful using DMSO. DMF, dimethylformamide, is another good polar aprotic solvent. And then HMPA, hexamethylphosphoramide, is another good one. We don't use this one so much anymore, HMPA, because it's also a pretty strong carcinogen. And so in my laboratory anyway, if we ever have to use HMPA, we use small amounts of HMPA in some other solvent to just try to improve the solubility. We don't really run a lot of chemistry in HMPA, in pure HMPA anymore. Okay? So these are some things that you need to know. So you need to know these polar aprotic solvents. You need to know that these polar aprotic solvents will favor SN2 chemistry. Okay? They make the nucleophile better. They favor SN2 chemistry. You need to know that the polar protic solvents, like water and alcohols, favor SN1 chemistry, not SN2 chemistry. Does that mean I can't do SN2 chemistry in alcohol? Absolutely not. I can. We're talking about what is favored when we have to make a decision about a mechanism. Okay? For the polar aprotic? Yes. For right now. Now, let's say we take our sodium bromide and we dissolve it into acetone. And we can do that. We can get so much sodium bromide into acetone. It turns out that the sodium is still stabilized because you've got the oxygen atom with the lone pairs of electrons that can solvate that sodium cation. However, do we have hydrogen atoms that can hydrogen bond to the bromide? It's absent. So yes, of course, there's solvent around it. It forms a shell. There's a positive end to this, right, that can kind of interact. That would be like a dipole ion interaction, right? What do we know about dipole ion interactions compared to hydrogen bonds? Stronger or weaker? Weaker, right? So we have a dipole ion interaction here. It's much weaker than a hydrogen bond. So is it going to be easier for it to get out of the way, or is it going to be harder? Much easier, right? And in fact, in solvents that are polar aprotic, we consider the nucleophile to be naked. It doesn't have its clothes on. Okay? It can react really quickly. Okay? You will hear chemists talk about naked ions all the time. Okay? I don't know who came up with this stuff. Okay? But when you hear me say a naked anion, you know what I'm talking about. It has a very loose solvent shell around it. Okay? So would you predict that the chemistry with sodium bromide would be faster or slower in water? Slower. It would be faster in something like acetone or DMSO or THF, right? Because you would have the naked anion. Okay? Now in polar aprotic solvents, it's exactly the opposite. We see exactly the opposite effect. Fluoride turns out to be a better nucleophile than chloride. Chloride turns out to be a better nucleophile than bromide. And bromide is a better nucleophile than iodide. Because fluoride is small, right? It doesn't have much steric hindrance to get to the carbon atom. It's naked. It's small. It can get there really quick and do the chemistry. So polar aprotic solvents, as we go down a family, nucleophilicity decreases. In polar protic solvents, as we go down a family, nucleophilicity increases. Okay? Very important. The trend changes as you go up and down a column depending on the solvent. So solvent has an effect here. Okay? Let's do another thought experiment. Here we have cis 1-bromo-4-methyl-cyclohexane. It's got a mirror plane, so there's no stereochemistry in terms of R or S, but there is stereochemistry. The methyl group and the bromide are cis to one another, meaning what? They're on the same side of the plane, right? And here we have hydroxide, and here we have water. What would you predict the outcome of this reaction? In both cases, you're going to get an alcohol. Water will react with an alkyl halide to produce an alcohol. Hydroxide will react with an alkyl halide to produce an alcohol. The products are going to be the same. What will you predict about the stereochemistry here? Okay, so you're going to predict that for the hydroxide, the stereochemistry will invert. And you'll end up with the hydroxide, or the OH and the CH3 to be trans to one another. Okay? All right? It's a pretty good prediction. So the mechanism must be what? How about for the bottom one? What will we end up with? Do I have a strong nucleophile? No. Water is also a solvent, so is it polar protic or polar aprotic? Polar protic. Polar protic solvents favor what kind of chemistry? SN1 or SN2? SN1. So what would we predict? Nothing happens to this stereocenter, right? No chemistry is occurring there. But what happens here? I can get partial inversion or I can get complete racemization. But in both cases, I'm going to end up with two products, right? One of those products would be where the OH and the methyl group are on the same side. That's an H. Sorry about that. In the top example, if the top example is correct, if Jack's prediction of this being SN2 is correct, when he goes and does the analysis of this molecule, it better be 100% trans. And if it is, then his prediction was correct. If he sees something like this, the prediction is incorrect, right? But his prediction is correct. If you actually go run this experiment, you'll see it. Strong nucleophiles for secondary alkyl halides favor the SN2 chemistry. For weak nucleophiles, they favor the SN1 chemistry. Okay.
I have a question.
Yes, sir.
If you go back, one of the points said that
I'm sorry.
that ROH group was a weak nucleophile.
Which?
Weak nucleophiles such as H2O and ROH
Mm-hmm.
favor SN1.
Yep.
So, but then on the picture it has OH as a strong nucleophile.
OH minus is a strong nucleophile.
Okay.
But H2O is a weak nucleophile.
Yeah. I got that. So if it was just, so if that OH was connected to like a
Well, but ROH is still, the oxygen is neutral, just like in water.
okay.
It's just one of the hydrogens has been replaced with a carbon. Remember, alcohols are just derivatives of water, so the chemistry is very similar. Okay, good question. All right, we're running out of time again. So I'll finish this up and get it on YouTube. Let me just mention a couple things before we go. That's why I've got to finish early. On Friday, we're going to do an inverted lecture. I will come in and we'll work a couple of problems before we do that, but more importantly, I'm going to do a demonstration, okay, on the effect of leaving group on SN1 chemistry. It's part of the video project, so you need to bring a device, either your phone, tablet, or whatever, that you can record a video, okay? And I will give you instructions on what to do to put your video project together. You just need to record the video right now. I don't want you worrying about the video project until after the exam, okay? But we're going to do the demonstration. You'll record the video. We'll go down that road. I will not be here Monday and Wednesday of next week. So you will have a sub on Monday, and somebody will come in and administer the exam on Wednesday, which means I'm not going to be available to do a pre-exam get-together next week, which I would typically like to do. So I'm going to offer a couple of options. Number one, tomorrow evening, we can have a pre-exam kind of lecture because we've already covered all the material we're going to need for the exam, okay? So if you can come, that's fine. If you cannot come, Monday evening or Tuesday evening, I will do a Zoom session, okay? Zoom allows you to connect with me, video, and I can answer any questions I can. I haven't decided on what times those will be. I'll be in Milwaukee. It will be later in the evening, like 8 o'clock, but I will make that available, so I'll send out a link about that, okay? So I apologize for not being here, but got to go. So, but I'll do my best to make it available to you, okay? Or to make myself available to you.
So our video project's not going to be due the Friday after the test.
No, it won't be due the Friday after test.
That's what it says in the syllabus.
It's what it says in the syllabus, but I had, that will be,
Sweet.
yeah, so don't worry about it. When I get back, we'll talk about it.
I'm not going to worry at all.
All right. Everything in the syllabus other than the exam dates are subject to change a little bit. So